Welcome to the MOOCs course Advanced Thermodynamics. The title of this lecture is Models for Excess Gibbs Energy Part 2. Since it is a continuation of previous lecture, we will be having a kind of recapitulation of what we have seen in previous lecture. In the previous lecture, we were discussing Ohm's expansion, and then by applying some kind of limiting conditions or restrictions, we reduced this Ohm's expansion to the van Laar equation, or otherwise we derived van Laar equation by making some kind of simplification to this Ohm's expansion. That is what we have seen, and then for those van Laar equation we have also developed activity coefficients, etc. Those things we have seen, and those things we have seen for a binary system. Then not only from the Ohm's expansion part of view, but also individually also we have derived the van Laar equation, and then cross check that we were getting the same van Laar equation from the Ohm's expansion as well, right. So, now what we do in this lecture, we will be obtaining Margulies equations and then Scatchard model equations, etc. for excess Gibbs energy from this same Ohm's expansion that we have written for a binary mixture, right. So, let us start with Margulies equation. Before directly going into the Margulies equation, what we do, we will have a kind of recapitulation of what is this Ohm's expansion, because from this Ohm's expansion only we are trying to get all the details, right. Ohl expressed this excess Gibbs energy of a binary solution as power series of Z1 and Z2. These Z1 and Z2 are known as nothing but effective volume fractions of two components, that is also we have seen. And then this GE for a binary solution, they have written as a kind of power series of Z1 and Z2, and then Z1 is nothing but x1 q1 by x1 q1 plus x2 q2. This is what we have seen, and Z2 is nothing but x2 q2 divided by x1 q1 plus x2 q2. q1 q2 are nothing but the size of the molecules that are present in the species 1 and species 2 respectively. x1 and x2 are nothing but the mole fraction of that particular component 1 and 2 that are present in the liquid solution. This is what we have seen. So, then what is this expansion? That we have seen that GE by RT x1 q1 plus x2 q2 is equals to this one, right. We have written only up to fourth power terms only we have written, and then this series continues actually, where Z1 is given by this one and Z2 is given by this one. They indicate effective volume fraction of two components. Further, this A12 and then A112, A122, A111, etc. whatever these A parameters are there, they indicate the interaction. They indicate the kind of interaction between those molecules. Let us say A12 indicates the interaction between one molecule of species 1 and then another molecule of species 2. Similarly, A112 indicates the interaction between two molecules of component 1 and then one molecule of component 2, like that all these A parameters are indicating. So, primarily this is having two constants A and then Q types of constants it is having. These are the kind of some kind of significance it is having from the interactions point of view as well. That is the reason it is one of the better expansion, though it is not having a kind of strong theoretical background to derive it, unless we make some kind of drastic assumptions. And it is having two constants A and then Q types of constants. Q constants indicates the size of the molecules, and A constant indicate the some kind of interaction amongst the molecule. Okay. If you consider binary solution of two components whose molecular sizes are not much different, that is when you take q1 is equals to q2 in Ohm's expansion, right. Then when we neglect terms higher than the fourth power in mole fraction. So, actually we are having terms in this expansion, we are not having any terms more than fourth power, right. So, we are having only up to fourth power terms. If you include all these terms and then you write q1 is equals to q2, because we are taking for molecular sizes are not much different, then whatever this expansion is there, that is nothing but 4 suffix Margulies equations, right. And then once we have this one, you apply this one RT ln gamma is equals to GI bar E, then simplify this Gi bar E is nothing but dou by dou Ni Nt Ge. So, this Ge is nothing but the right hand side multiplied by RT x1 q1 plus x2 q2, that if you substitute here, differentiate and simplify, then you will get and then you equate that one part to the RT ln gamma I. So, then you will get expression for ln gamma I for 4 suffix Morgul's equation. Remember in previous lecture what we have done, we have taken only up to this part. We have taken only up to this part, that is we have taken only terms which are having power of z power 1 and z power z1 power 1 and z2 power 1 only, that is we have not taken any third power or higher power terms, we have not taken. That is what we have done one simplification. Another simplification we have done, q1 is not equals to q2, then whatever this expression, simplified expression that we got, we called it as a kind of Wandler equation, which were also having two constants a and b, or a prime b prime constants only we were having, right. So, those constants again written in terms of this a12 q etc., a12 q1 q2 etc., in those terms only we have written this a b constant. So, from this point of view, if you take only this part of equation, Ge by RT x1 q1 plus x2 q2 is equals to 2 a12 z1 z2 and then z1 z2 also if you substitute with these things and then simplify, then you will get Ge by RT is equals to 2 x1 x2 q1 q2 divided by x q1 plus x2, then you will get Ge by RT is equals to 2 a12 x1 x2 q1 q2 divided by x1 q1 plus x2 q2, that is what you get. If you write Ge by RT is equals to 2 a12 x1 x2 q1 q2 divided by x1 q1 plus x2 q2, this is what you get when you take only up to second power terms and then not taking higher power terms, then substituting z1 z2, then Ge by RT you get this one, this is nothing but Wandler's equation. And then here you see it as kind of two this a12 q1 q2 three parameters are there, but activity coefficient when you derived you got only two parameters a and b, because there this ratio of q1 and q2 we have taken rather taking individually q1 q2, because in general we have also seen the ratio of this molecular sizes molar volume of these components is much more important compared to the individual size of this molecule. So, that is the reason we are having this one. So, this was the Wandler equation that we have seen in the previous lecture, and then corresponding ln gamma 1 and ln gamma 2 also we have derived, we have seen some examples as well. Then not only from Mole's expansion, individually from the physics of the problem point of view also, when two pure liquid solutions are mixed at temperature T and pressure P and then forming a solution non-ideal solution at same temperature and pressure same temperature T and pressure P, then whatever the process that you have done, you have taken in a 3-step processes and then derived that same Wandler equation again. So, then you got the same equation. So, that way also we have seen. So, now in this equation we are starting with the Morgul's equation. So, rather starting with 2 suffix Morgul's equation, which we have already seen previously. 2 suffix Morgul's equation is nothing but Ge by RT is equals to A x1 x2, right, A x1 x2. This is what 2 suffix Morgul's equation. This we have seen in one of the previous lecture, but we rather going with the simplest one, what we are doing, we are taking the tougher one, that is up to 4th powers in mole fraction, those terms will be including, and then what we do, gradually we come back to the smaller level, that is 3 suffix and then 2 suffix Morgul's equation by making some alternative by making some kind of adjustments or simplifications. Okay. Adjustment simplification in the sense, let us say you are taking up to 4th power series, then it is 4 suffix Morgul's equation. If you take only up to 3rd power in mole fraction, then it will be 3 suffix Morgul's equation, right. So, those kind of things would be there here. Okay, that is the only difference. If you take only up to 2 power series in mole fraction, then without taking q1 is by and further taking q1 is equals to q2, then you will get the 2 suffix Morgul's equation, which would be same as the Ge by RT is equals to A x1 x2. A would be function of some A12, q1, q2, etc. Now, in the Morgul's equation, what we have, the all qi and qj's are same, that is q1 is equals to q2. So, we are taking same size molecules. So, when you do this thing and then you try to obtain the ln gamma 1 and then ln gamma 2 for that expression, whatever that we have written Ol's expansion in power series by retaining the 4th power terms of mole fraction as well, and then by applying this RT, ln gamma I is equals to dou by dou Ni of Nt Ge at Tp Nj. This when you apply and then you do for binary mixture having component 1 and 2, then you will get ln gamma 1 this one, ln gamma 2 as this one. I am not doing it, you can take it as a kind of practice, because such a simple differentiation and then rearrangement of the components. Then here rather writing this parameters constants as A12, A122, A112, etc., those kind of parameters, we are writing A prime, B prime, C prime, because this A prime, B prime, C prime are again related to this A parameters and then Q parameters. Remember, in this case what we are taking, q1 is equals to q2 is equals to q. So, A prime is nothing but q multiplied by 2 A12 plus 6 A112 minus 3 A122 plus 12 A112 minus 6 A112, and then B prime is nothing but q multiplied by 6 A122 minus 6 A1 minus 6 A112 minus 24 A112 minus 8 A122 plus 24 A112. This is what you get, and then C prime is simply q multiplied by 12 A112 plus 12 A122 minus 18 A112. Now, this A point of view also, this suffix of A, we can understand this A112, that means it is including the interaction between 4 molecules, and then 4 nearest molecules being 3 from the molecule 1, 3 from component 1, and then 1 molecule from component 2, that is what it means by. And then this indicates interaction between 4 nearest molecules, out of which 3 are from component 2 and 1 is from component 1. And then this is indicates interaction amongst 4 molecules, out of which 2 molecules are from component 2 and 2 molecules are from component 1. So, this is what we understand, same is like this. So, that means if you do not include this C and then include only this A prime and B prime, so then it will become 3 suffix Morgul's equation. And then if you include only A prime and then you do not include any of other things, then it will become 2 suffix Morgul's equation. Right. And then also when you say including only A prime, so 2 suffix Morgul's equation, that means only this whatever these terms will also be disappearing, they will not be present, because 2 suffix Morgul's equation takes interaction only between 2 molecules only. 3 suffix Morgul's equation, then interaction because of because of interaction between 3 molecules will also come into the picture. So, under such conditions what happens, let us say 3 suffix Morgul's equation if you take, then this term would be there in A and this one would also be there, this one would also be there, but these 2 will not be there, because 4th power we are not including terms, right. And then B also, this term would be there, this term would be there, these 2 terms would not be there, even this third term will also not be there, and then this will not be there at all. This whatever this cross now I am showing, those terms would be there if you are including if you are including or if you are expanding the whole if you are having the whole series up to fourth power of mole fractions, then only this cross terms will also be there, otherwise only the tick terms would be there. So, that will become 3 suffix Morgul's equation. If you include the cross terms also, then that will become this 4 suffix Morgul's equation. Let us say if you have a 2 suffix Morgul's equation, so these terms further they will reduce. No, this will also be not, all the 8 parameters with having 3 suffix will not be there, I, j, k. So, if these things are not there, so then that is 2 suffix Morgul's equation, I, j, k, l also, right. If only in addition to I, j, k, l, if you have a, x, y, z, these things also if you do not have, then that is a kind of 2 suffix Morgul's equation. If you have a, x, y, z and then a, p, q, these kind of terms, I am just indicating the suffix differently so that to understand, then it is known as the 3 suffix Morgul's equation. If you have only a suffix pq kind of term, then it is a 2 suffix Morgul's equation. If you have all these a pq kind of interactions, a xyz kind of interaction and then a I, j, k, l kind of interaction, then that is known as the 4 suffix equation. So, that means that is including all these terms. Okay. So, it is just to explain how this from 4th suffix Morgul's equation we can get back to the 3 suffix Morgul's equation and 2 suffix Morgul's equation. That is the point of this description, right. If the expansion is truncated after quadric terms, the equation is called 4 suffix equation or 4 suffix Morgul's equation, that is having all these a prime, b prime, c prime terms. If the case in the case of limiting experimental data is there and it is common to truncate the expansion after cubic terms. So, that means c prime etcetera, those terms should be 0. If the c prime is 0, so then whatever the equation is there, that is known as the 3 suffix Morgul's equation. Not only c prime, as I mentioned, all these parameters which are having the interaction, this fourth power kind of thing, these things will also be not there. Okay. Then in addition to this c prime, if you exclude in a prime, b prime also whatever this cross term where interaction amongst 4 molecules are shown, then that equation would become 3 suffix Morgul's equation. So, if the mixture is simple containing similar components, it is sufficient to truncate quadratic terms, that is second order terms, then the equation is called 2 suffix Morgul's equation. That means, under such conditions, in addition to c prime is equals to 0, b prime would also be 0, then we call it as a kind of 2 suffix Morgul's equation. In addition to this one, in the a prime we will not be having these terms which are having interaction between 3 molecules, right. So, in the 2 suffix Morgul's equation, if you do not take q1 is equals to q2, then we will be having kind of a Wandler equation. So, what is the relation between Wandler equation and then 2 suffix Morgul's equation? Rather relation, what are the difference, that point of view, if you see 2 suffix equation we are taking q1 is equals to q2 is equals to q, whereas in the Wandler equation we are taking q1 is not equals to q2. So, that is the one primary difference between this 2 suffix Morgul's equation and Wandler equation respectively. Okay. Despite assumption of similar molar volumes, that is q1 is equals to q2, Morgul's equations are frequently used for all sorts of liquid mixtures regardless of relative sizes of different molecules, and adaptability of Morgul's and Wandler's equation lies in their simplicity, that ability to represent experimentally determined activity coefficient with only a few constants, right. Wandler equation also we are having only 2 constants a and b, and then 3 suffix, if you take only 3 suffix Margulis equation, then also we have only A prime and B prime, 2 constants are sufficient to represent successfully the experimentally determined activity coefficient with respect to the mole fraction of the component. Also, when the data are scattered or scarce, then these models, whatever the 3 suffix Margulis equation and then Van Laar equations are there. So, they are used for smoothing of the data as well as for some kind of interpolation or extrapolation, so that to get the data, additional data which is not obtained by the experimental results. So, such is the advantage of these two equations, 3 suffix Margulis equation and then Van Laar's equation. Now, by using 3 suffix Margulis equation, we take 3 examples: acetone chloroform mixture and then acetone methanol mixture and then chloroform methanol mixture at 50 degree centigrade. Then whatever this activity coefficient of acetone and then chloroform here in this case, and then in this case acetone methanol, and then in this case chloroform methanol versus mole fraction of one of the component is presented. So, then you can see these circles or whatever the these unfilled circular symbols are there, they indicate the experimental results, and then the solid lines indicate the theoretical results or the 3 suffix Margulis results whatever we have. So, that if you see, you can see the excellent matching between these 3 suffix Margulis equation and then experimental results for the entire range of mole fraction from 0 to 1, except in this case of chloroform methanol, where there is a kind of some amount of discrepancy at mole fraction of chloroform is very small, right. So, that is the advantage of this 3 suffix Margulis equation, and then previous lecture we have seen advantage of Van Laar equation, where we have only 2 constants associated with this with the activity coefficient of these equations, but still we are able to represent experimental data with much better accuracy. And remember, all these 3 solutions show a kind of azeotrope at certain temperature, especially at 50 degree centigrades, close to that one, right. Despite of that one, the ln gamma I versus xi or xj information has been successfully represented by 3 suffix Margulis equation. Okay. Here we can see this A prime B prime parameters. In the case of S10 chloroform, both are having negative, that means large negative deviation from ideality. And then acetone methanol mixture, we can see both of them are positive A prime B prime values are there. So, that means large positive deviation from ideality is observed. In the case of chloroform and methanol, we see A prime is positive and then B prime is negative. What does it mean by towards the chloroform rich side we have a kind of a positive deviation, whereas towards the methanol rich side we have a kind of a negative deviation from the ideality, right. So, this is about 3 suffix Margulis equation and their applicability compared with the experimental results. Now, we take Scatchard-Hammer equation. Now, the Ol's expansion, what we do? We truncate expansion after third order terms, but will not be taking Q1 is equals to Q2, rather we take Q1 by Q2 is equals to V1 by V2. That is, if you compare with the Van Laar equation, what we have taken? We have taken Q1 is not equals to Q2, same thing we are doing here, and then we have taken the terms or discarded terms after the second order terms, right. But now here we are taking the same Q1 is not equals to Q2, and then not only second order terms, we are also including the third order terms, but truncating the terms after the third order terms. So, it is a kind of improvement over the Van Laar equation if you consider in terms of the interactions, because higher terms are included compared to the Van Laar equation, rest all assumptions are same, Q1 is not equals to Q2 and all that. In the Van Laer equation we have taken only up to second order term, but now we are taking up to third order term also. So, in that way if you see it is a kind of improvement over Van Laer equation, but gradually if you see it has not been found a better adaptability especially with the experimental results, unfortunately, though it is a kind of improvement over Van Laer equation, especially from Ol's expansion point of view, where we are taking up to third order term as well in this Scatchard-Hammer equation. Despite Van Laer equation, we are taking only up to second order term, it is matching very well with the experimental results, but here Scatchard-Hammer equation, though we are taking up to third order term, the experimental matching is not so good, right, where V1 and V2 are molar volumes of pure liquids at the temperature of the solution. Then if you apply this RT ln gamma I is equals to dou by dou Ni of Gi bar E at constant Tp Nj, and then apply this Ol's expansion whatever Ge by RT x1 q1 plus x2 q2 is equals to up to third order term. Third power terms, if you include those terms, if you simplify you get the Ge, and then you differentiate Ge with respect to N1 and then equate it to the RT ln gamma 1, then you will get ln gamma 1 this one. Similarly, if you do, you get ln gamma 2 this one. Here we have A prime B prime terms, right, this A prime B prime terms, and then in addition to that one we are also having V1 by V2 terms or V2 by V1 terms also there, where this A prime B prime are nothing but given by these two equations, right. A prime is equals to V1 multiplied by 2 A12 plus 6 A112 minus 3 A122, and B prime is V1 multiplied by 6 A122 minus 6 A112, right. So, this is what we get, and then this equation uses only two adjustable parameters like Van Laer equation and then 3 suffix Margulis equation. Here also we have only two parameters, but have not received much attention in the extensive literature on VLE, unfortunately. And then this can be seen as a kind of a intermediate between Van Laer equation and then 3 suffix Margulis equation, because Van Laer it is including only second power term only, it is including 3 suffix Margulis equation, it is including third power or third order terms also it is including, and then Van Laer equation we are not taking q1 is equals to q2, but in the 3 suffix Margulis equation we are taking q1 is equals to q2. So, this Scatchard-Hammer equation is a kind of intermediate where we are taking up to third order or third power terms, but q1 is not equals to q2, one part from here and then one part from here. So, that is the reason it is a kind of intermediate of this one. Despite of that one, it does not receive much attention in the literature. So, all these three equations are having two adjustable parameters A prime and B prime. So, that is about this Scatchard-Hammer equation. Now, quickly we see a few example problems, right. So, a mixture of benzene and isooctane system is described by this excess Gibbs energy function at 200 degrees centigrade and 11.6 bar. So, assume these constants A and B are independent of temperature, pressure and composition. So, describe whether this model is thermodynamically consistent or not. So, though we have seen such kind of problems, so we have them once again. So, thermodynamic consistency, we know that sigma xi d ln gamma I should be 0. So, here we are having two components. So, for that two components Ge is given by x1 x2 multiplied by A plus B multiplied by x1 minus x2. So, this is the Ge is given. We need to know ln gamma 1 and ln gamma 2, because for these two components we have to see whether this x1 d ln gamma 1 plus x2 d ln gamma 2 is becoming 0 or not, that we have to check. If it is becoming 0, then this model is thermodynamically consistent, that is what we can say. So, RT ln gamma 1 is nothing but dou by dou Ni of Nt Ge Tp Nj, or dou by dou Ni Nt Ge is nothing but Gi bar, right. Gi bar E is not given, so that is the reason we are writing dou by dou Ni of Nt Ge, right. So, this dou by dou Ni now we are writing for component 1. So, RT ln gamma 1 is equals to dou by dou N1 of Nt is as it is, this part is nothing but Ge, right, and then Ge we are having x1 x2 terms, that we are writing a kind of N1 by Nt and then N2 by Nt, that is what we are having. So, this parenthesis term A plus B multiplied by N1 minus N2 by Nt. So, LCM when we do, we have A Nt plus B N1 minus N2 divided by Nt, and then in place of x1 x2 we have N1 by Nt, N2 by Nt. So, that is N1 N2 by Nt square. So, now further if you simplify, we have dou by dou N1 of N1 N2 Nt A plus B N1 minus N2 N1 N2 divided by Nt square at constant Tp N2. Now, differentiation of this term we have to do. So, further Nt if you can write N1 plus N2, it will be easy to differentiate, right. Then we have wherever Nt we are having, we are writing N1 plus N2, because we are differentiating with respect to N1, and then Nt is nothing but N1 plus N2. Then we have the differentiation of first term is N1 plus N2 multiplied by 1 into N2 minus N1 N2 multiplied by 1 plus 0 divided by N1 plus N2 whole square. Similarly, differentiation of this term is this denominator N1 plus N2 square whole square. So, that is N1 plus N2 whole power 4, and then in the numerator N1 plus N2 whole square, and then differentiation of numerator term minus numerator term as it is, and then differentiation of denominator term, that is what we are having here, right. So, when we do this one, so then what we have from the first term N1 N2 plus N2 square minus N1 N2 divided by N1 plus N2 whole square. So, this is cancelled out, and then here N1 plus N2 whole square is as it is, differentiation of this one is 2 N1 N2, and then differentiation of this one is simply N2 square. Here N1 minus N2 multiplied by N1 N2 is as it is, differentiation of this term is 2 into N1 plus N2 multiplied by 1. So, 2 into N1 plus N2. So, this is what we are having. So, those terms we segregate like this. So, A N2 by Nt whole square plus B multiplied by 2 N1 N2 minus N2 square divided by N1 plus N2 whole square minus 2 N1 N2 multiplied by N1 minus N2 divided by N1 plus N2 whole cube. This is we are writing simply so that wherever it is Nt square terms are there. So, N1 N2 by Nt square you can write x1 x2. Similarly, N2 square by Nt square you can write x2 square like that. So, for that purpose we have written like this. So, then we have Ax2 square plus B multiplied by 2 x1 x2 minus x2 square minus 2 x1 x2 multiplied by x1 minus x2, that is what we get. When you simplify, you will get A plus 3b x2 square minus 4b x2 cube, this is what you get. So, that means ln gamma 1 is nothing but A plus 3b by RT x2 square minus 4b by RT x2 cube. So, ln gamma 2 also similarly we can obtain, but analogously from here also we can write that ln gamma 2 should be A minus 3b by RT x1 square plus 4b by RT x1 cube. So, that is what you will get for ln gamma 2. Okay. Similarly, you can do otherwise RT ln gamma 2 is equals to dou by dou N2 of Nt Ge at constant Tp N1 if you do, and then simplify, then you will get, or analogously if you have to the level that you can analogously write, then you can write this. So, then for thermodynamic consistency we have to see x1 d ln gamma 1 by dx1 plus x2 dln gamma 2 by dx1 should be 0. So, if you write in place of dx1 minus dx2, because it is a binary system, so dx1 plus dx2 is equals to 0, that means dx1 is equals to minus dx2. So, then the term minus x2 dln gamma 2 by dx2, if you take to the right hand side, you will have x2 dln gamma 2 by dx2, right. So, either way you can check, you can do this one and then you can do this one, add them together to see whether it is 0 or not, or otherwise individually you find out this one and this one, you check if both of them are equal or not. So, dln gamma 1 by dx1 is nothing but d by dx1 of ln gamma 1 is nothing but a plus 3b by RT x2 square minus 4b by RT x2 cube. In place of x2 I am writing 1 minus x1 because this differentiation I have to do with respect to x1, right. So, then you get this expression. Similarly, dln gamma 2 by dx1 is nothing but d by dx1 of a minus 3b by RT x1 square plus 4b by RT x1 cube. So, here I have to differentiate with respect to x1. So, what I am doing, I am not writing this x1 as 1 minus x2, that is not required. So, we have this term. So, now if you have x1 dln gamma 1 by dx1 plus x2 dln gamma 2 by dx1, that means if you multiply by this one x1 and then this one you multiply by x2 and then simplify, then you have these terms, right. So, when you see simplify these terms, you have from these two terms we have minus 6b by RT x1 x2 remaining. From this term you have a minus 6b x1 x2 by RT, and then from these two terms what you have a if you take 3 x1 x2 as a common, then 3 x1 x2 multiplied by x1 plus x2 multiplied by 4b by RT is there. So, x1 plus x2 is 1. So, this is nothing but 12 b x1 x2 by RT. So, this is minus 12 b x1 x2 by RT cancel out. So, we have 0. So, that means we get, since we get x1 dln gamma 1 by dx1 plus x2 dln gamma 2 by dx1 is equals to 0, we can say whatever the Gibbs function that is given, GE is equals to x1 x2 multiplied by a plus b multiplied by x1 minus x2 is thermodynamically consist. And then this equation, if you recollect, is nothing but is also known as 3 suffix Margulis equation, right. And then these activity coefficients are known as the corresponding activity coefficients of 3 suffix Margulis equations. So, quickly we take another example in similar lines. Activity of component 1 of a binary mixture is given by a1 is equals to x1 exponential of alpha x2 square, then obtain the activity of the component 2. So, what we have, again we will be using sigma xi d ln gamma I is equals to 0, this expression we use, and then we try to obtain the activity of the second component, right. So, this a1 is given like this. So, what we are doing, we are taking ln either side and then right hand side we are expanding, right hand side we are expanding. So, we have ln a1 is equals to ln x1 plus alpha x2 square. Now, we need d ln a1 in order to substitute here, right. So, ln ai or ln gamma I also you can use, this Gibbs de Homme equation is same anyway. We need d ln a1. So, what we are doing, the right hand side also we are doing differentiation. So, d ln x1, d of ln x1 is nothing but dx1 by x1 plus alpha is constant, and then d of x2 square is nothing but 2 and this x2 what I am doing, I am writing 1 minus x1. So, that we have 2 multiplied by 1 minus x1 minus dx1 will be having, and then alpha is constant as it is. So, that means d ln a1 is equals to dx1 by x1 minus 2 alpha 1 minus x1 dx1, this is what we can write. So, actually 1 minus x1 we can write x2, that we will write in the next step. So, but we have x1 d ln a1 plus x2 d ln a2 is equals to 0, this is also Gibbs de Homme equation. You can have in terms of activity coefficient or in terms of activity it is same. So, we need a2. So, how we rearrange this equation? We rearrange it as d ln A2 is equals to minus x1 by x2 d ln A1. So, this equation, if you substitute here in place of d ln A1, we have this expression, right, minus dx1 by x2 d ln A2 is equals to minus x1 by x2 multiplied by d ln A1. This is d ln A1. So, first two terms when you join together, you have minus dx1 by x2 because x1 and x1 cancels out, and then minus of minus plus 2 alpha 1 minus x1 x1 by x2 dx1. So, this 1 minus x1 and then this x2 are same. So, we have this expression, right. So, d ln A2 is equals to minus dx1 by x2 plus 2 alpha x1 dx1. So, this one I am writing minus dx1, I am writing as dx2. So, dx2 by x2 minus 2 alpha 1 minus x2 I am writing for x1, and then in place of dx1 I am writing dx2 minus dx2. That is the reason here minus we are getting, because for binary system dx1 plus dx2 is equals to 0. So, that it can easily be integrated, that is the purpose we are writing in terms of any one. So, that is in terms of x2 we are writing. So, ln A2 if you integrate above equation, you get ln A2 is equals to ln x2 minus 2 alpha 1 minus x2 whole square by 2 multiplied by minus 1 plus c. That means, ln A2 is equals to ln x2 plus alpha x1 square plus c, and then when x2 is equals to 1, then activity should be 1 or activity should be equals to the mole fraction. So, mole fraction is equals to 1 now, right, because when x2 is equals to 1, it is a pure solution. So, for pure solution is always ideal solution, and then for ideal solution activity is equals to the mole fraction, right. So, that means A2 is equals to mole fraction, and mole fraction here is nothing but 1. So, that you substitute here, you get C is equals to 0, right. So, that means A2 is equals to x2 exponential of alpha x1 square. So, this is what you get. So, now quickly we take another simple example problem before winding up this lecture. A binary liquid mixture of component A and B obeys the following model of excess Gibbs energy. GE is equals to 1 by AXB plus 1 by BXB whole power minus 1 plus C XA XB multiplied by XA minus XB whole square, where A, B and C are constants. So, this question is again similar to example 1. So, first obtain the ln gamma A and then ln gamma B, then check thermodynamic consistency is existing or not, right. So, it is quite similar problem. It is quite similar problem that we have already done. So, GE is given by this one, and then we know RT ln gamma A is nothing but dou by dou Na of NT GE, and then RT ln gamma B is nothing but dou by dou NB of NT GE, that is what we know. So, this GE if you differentiate, that is RT ln gamma A is equals to dou by dou Na of GE is this one. So, this GE we are differentiating with respect to Na for ln gamma A purpose. So, this entire equation rather writing in XA XB, we are writing XA is equals to Na by NT, and then XB is equals to NB by NT. NT is total number of moles, Na and NB are nothing but the number of moles of A and B components present in the solution, whereas XA and XB are nothing but the mole fraction of component A and B that are present in the solution. So, when you differentiate and then simplify, we get this equation. I am not doing it because so many of them we have already done. So, you can take up and then try to do yourself. Similarly, RT ln gamma B is equals to dou by dou NB of NT GE. If you do, then you will get RT ln gamma B is this one. Simply differentiation and then rearrangement. So, straightforward one can get. So, now we can we have to do thermodynamic consistency check. For that purpose, what we do? We check sigma xi dln gamma I is 0 or not. So, that means xa dln gamma A by dxa should be xb dln gamma B by dxb. So, first term RT ln gamma A whatever we derived. So, that one we are differentiating with respect to xa. So, d by dxa of right hand side term of ln gamma RT ln gamma A term expression that previously we derived this one. So, differentiation of this first term is nothing but 2 AB xb divided by AXA plus BXB multiplied by d by dxa of this particular term. So, that is this one multiplied by d by dx of Bxb divided by Axa plus Bxb, right. I am differentiating with respect to Xa. So, that is the reason all the xb terms I am writing 1 minus Xa plus C, and then differentiation of this xb square term is nothing but 2 xb into minus 1. So, xb I am writing 1 minus Xa. So, 2 1 minus Xa multiplied by minus 1, and then remaining 2 terms are as it is, but I am writing in place of xb 1 minus Xa I am writing. Then C xb square is remaining as it is. Differentiation of 2 multiplied by 2 xb minus 1 is nothing but 2 multiply d by dx of d by dxa of 2 into 1 minus Xa, that is minus 2 we are having, that is 2 multiplied by minus 1, and then third term is as it is. Similarly, C xb square and then 2 xb minus 1 terms same, and then differentiation of third term, that is d by dxa by then differentiation of third term, that is d by dxa of 6 into 1 minus Xa minus 5 is nothing but minus 6. So, that is what we are having. Now, if you rearrange this equation, then you will get simply this term, quite a lengthier term, you do not need to further simplify anyway. Only thing that we have to see the other term xb dln gamma B by dxb is also same or not, that is what we have to find out. So, that we do know. So, whatever xa dln gamma A by dxa we got, I am rewriting here just because we need it for comparison for the next step. So, dln gamma B by dxb, so RT dln gamma B by dxb that we are doing. So, whatever the RT ln gamma B expression that we had previously derived. So, that expression both sides we are differentiating with respect to xb. So, right hand side this is what we have on d by dxb of this term. So, now similar differentiation you do as we have done in the case of dln gamma A by dxa. So, here we are doing this second term, we are doing differentiation with respect to xb. So, we want to have all the terms in terms of xb. So, wherever xa is there, that you can write 1 minus xb and then do the differentiation and then simplify. So, then you have this term, this is nothing but xb dln xb dln gamma B by dxb. Now, by comparing these two equations, this is xb dln gamma B by dxb and this is xa dln gamma A by dxa, right. This we derived previous slide. So, we can see they are looking similar, but they are not same. We can compare one term, if one term is not matching, that means you do not need to compare rest of the term. Take the simplest one, last term here is 6 C xb square 6 C xa square xb multiplied by 1 minus 2 xb, whereas here the last term is 6 C xa xb square. So, here is it is xa xb square, here is it is xa square xb, and then here it is 2 xb minus 1, here it is 1 minus 2 xb. So, they are not same. So, they are not equal to each other. So, that means we say it is thermodynamically inconsistent. You can say whatever the GE expression is given, that is 1 by AXA plus 1 by BXB whole inverse plus C XA XB, and then what is that they have given? C XA XB multiplied by XA minus XB whole square multiplied by XA minus XB whole square. So, whatever this given GE form is thermodynamically inconsistent. Okay. References for this lecture are provided here: Engineering and Chemical Thermodynamics by Koretsky, Molecular Thermodynamics of Fluid Phase Equilibria by Prousnich et al., and then Chemical, Biochemical and Engineering Thermodynamics by Sandler, and Introduction to Chemical Engineering Thermodynamics by Smith et al. This entire lecture is available in this reference book. Some of the problems that we have solved are exercise problems of this book, Koretsky. Thank you.